Dear all, good morning. Now our course. Now we are going to discuss Unit 4. In this one, first lecture is orthonormal set of vectors. Overall, 26th lecture. In the last unit, that is third unit, we discuss orthogonal set of vectors or orthogonal and orthogonal complement, projection onto a line and projection onto a plane, and least square approximation. So now we discuss what is the orthonormal set. First, we recall what is the orthogonal set. The definition already you know this one. Let V be an inner product space, then a non-empty set. This is the set. Subset of vector space is called an orthogonal set. When it's called orthogonal set, if they are mutually orthogonal. Yeah, that is the inner product is 0. Any two vectors. When the I not equal to J, they are mutually orthogonal. When this is the inner product 0, you can say dot product is 0. Orthogonal means you can say inner product is 0, dot product. You have to take usual inner product. That is standard inner product. When this set is called orthonormal. See, in this orthogonal set, each vector length is 1. You can say the set is orthonormal. Like further, ui is 1 for 1 to n. Then S is called an orthonormal set. That means the inner product, whatever take ui uj equal to 0 if I not equal to j. In that way, 1 if I is equal to j. Yeah. When that inner product is 0, I not equal to j, I equal to j is 1. This is orthonormal. That orthonormal set. See, suppose the set is basis, then the set is called orthonormal basis. Simple, you can take suppose orthonormal set. Suppose any set, suppose u1, u2, un, it's orthogonal. Orthogonal. See now this is orthogonal. If you take this u1 by norm u1, u2 by norm u2. When you take u1 by norm u1, that is unit vector. That is un by norm un. This is unit vector. Each one is orthonormal. When the set orthogonal, if you divide each vector with that vector length, then the set is converted to orthonormal. Now we'll see example. So example 1, the standard basis, already you know standard. In Rn is with standard basis or usual basis. With standard basis is on orthonormal. Already you know standard basis means you know this is E1, E2, En. Suppose set is an orthonormal set. We know that E1, E2, En, suppose like where Ei is equal to, that means all components are 0 at ith element is 1. Where 1 less than or equal to I less than or equal to j. Sorry, n. For 1 less than or equal to I less than or equal to n. That one. Already we discussed this one. This is orthonormal set. See now, we know this is the basis. Basis on Rn means when that set is basis, you can say it's orthonormal basis. That means you can say this one is orthonormal basis of Rn. This is orthonormal basis. Now take another example, simple example. Suppose take this example 1 by root 2 1 comma 1, 1 by root 2, 1 comma minus 1 is an orthonormal set. In R2. If you need, you can check it. Say that each length is 1, this one, and dot product 1 into 1, 1, 1 into minus 1, 1, 1 minus 1 is 0. The dot product is 0 and the length is 1. Orthonormal set in R. Suppose this set is basis, you can say it's orthonormal basis. Suppose take 1, 1, 0, 1 minus 1, 2, 1 minus 1, minus 1. Suppose take this set. Now you can check this dot product of these two vectors. 1 minus 1, 0. This one also 1 plus 1, minus 1 minus plus 1. 1 plus 1, 2, minus 2, 0. And this also 0. They are mutually orthogonal. That means this is orthogonal set. Is it orthonormal? No, it's not orthonormal because the length of this vector is root 2. This length of vector is root 6. This length of vector is root 3. Is not orthonormal set. Not on orthonormal set. But it is an orthogonal set. On orthogonal set. Suppose this orthogonal set, but every orthogonal set we can write in the orthonormal set. That means divide this orthogonal. Now divide each vector with the vector length. Suppose this one, if you divide this is 1 by root 2, and this one is divided by 1 by root 6, divided with 1 by root 3. Then this set is converted to orthonormal. So now we'll see another one. Suppose take fourth example. Let V be the space of real valued continuous function on the interval 0 to 1 with the inner product. The inner product defined like 0 to 1 f of x into g of x dx. So now I am taking some two functions. Let f1 of x is root 2 cos 2 pi n x and gn is this one root 2 sin 2 pi n x. This set 1 f1 g1 f2 g2 and so on up to so on. It's infinite set is an orthonormal set. It's orthonormal means that each two functions is 0, two different function inner product is 0 and itself function is length is 1. For example, you could take suppose f1 of x. Now in general you can take fi. Fi of x is root 2 cos 2 pi ix and fjx gjx root 2 sin 2 pi jx. Suppose take see the inner part fi comma gj. Now 0 to 1 root 2 cos 2 pi ix into root 2 sin 2 pi jx, where I not equal to j. If I is equal to j, we'll see that one. I not equal to 0. f1 g1 like not f1 f1 g2 f2 g1 like. See now, see 0 to 1. Now root 2 into root 2 2. 2 into you can write 0 to 1 cos 2 pi ix into sin 2 pi jx dx. You know like this part, you know this one sin a cos b. 2 sin a cos b equal to sin a plus b plus sin a minus b. You know this one. Now you apply this one like 2 sin a sin b is equal to 2 into, that means 0 to 1 sin a plus b like sin a cos b 2 pi is common, j plus I x plus sin a minus b, j minus I, so 2 pi into sin 2 pi into j minus I x dx. Now integrate this one. The integration of sin is minus cos 2 pi j plus I x. The coefficient of x is dividing this one into 2 pi into I plus j. Again sin this one minus cos 2 pi into j minus I x divided by 2 pi j minus I 0 to 1. So when substitute 1, 2 pi j plus I. This j plus I number, some 2 pi, that's even number. Cos out pi into even number. This is always 1 minus 1 by 2 pi into I plus j. 2 pi into I plus j. See now, when substitute 0, minus minus plus, cos 0 is 1, that 1 by 2 pi into I plus j. This is 0. Again minus. Now when you substitute that even number, cos is odd function, cos of negative again positive. Whatever j minus I, if it whatever j is lesser, bigger number or I is bigger number. If it j is a bigger number, it's a positive. I is a bigger number, it can negative. Cos of negative again positive. That's a cos is odd function, even function. Whatever you get, that again we get 2 pi into some number, that's even number. Pi into even number is always 1, that is minus 1 by 2 pi j minus I minus that minus minus plus cos of 0 is 1, that 1 by 2 pi j plus I. That means this term is 0. That is 0. When you take, that means f1 g2 like this one. When the I not equal to j, this is 0. Now you can check it. That means f1 g1. No, each one, that fi j, the two vectors, two different one is 0. Now you can check it this one, same procedure, fi into fi, you get this is the one, and you can check it gi into gi, also 1, and this 1 into fi, you can check 1 into any vector, this is we get 0, and 1 into gi also 0. If any doubt, you can check it this one. And what about inner product of 1 comma 1 is 1. 1 comma 1 means 0 to 1, 1 into 1 dx. Integration of 1 is x dx. Suppose that this is that means actually this 0 to 1, 1 into 1 dx. That means x 0 to 1. That is the 1. 1 minus 0. This is 1. That means this set is an orthonormal set. Now, don't take this f1 g1 because you are take f I not equal to 0. F1 g2 like this one. Two different function f g. The orthonormal set. Suppose if you take I is equal to j, here this is 0, this again. Now if you take I is equal to j also, 0. That f1 g1 also 0. See now on theorem, let s equal to u1 u2 un subset of b and see now you can change this. Okay. Suppose if you take I is equal to j here, I is equal to j cos 2 pi ix sin 2 pi ix, like sin a cos, say sin a 2 sin a sin b. We know this formula, 2 sin a cos sin a cos a equal to sin 2a. Now use this formula. Again you get 0. This is a set It's orthogonal subset for an inner product space V over F. Then S is linearly independent subset of V. That means any orthogonal set is linearly independent subset. The orthogonal set must be subset of vector space, the linearly independent subset. So let B equal to U1, U2, N be on ordered basis. Ordered basis, any ordered basis. If V belongs to linear span of S, then V equal to I is equal to 1 to N via UI norm UI square into UI. That means V equal to, it's a linear span. This is some number and UI. That's a linear combination of the basis vectors. Okay, this is the important one. You can say any vector in a linear span. This is a coordinates actually. Coordinates of a this U1, U2, UN vectors. Coordinate. So now in particular, suppose this is an orthonormal set. This orthonormal set means that the length is 1. The length is 1. You can say V is, this length is 1. V comma UI into UI. Or equivalently for any vector in the linear span, that coordinates of vector with respect to basis B, this is the inner product. V comma U1, V comma U2. Like this one. Okay, I give you example on this. So like this one. Suppose, okay, next we'll discuss that example. So now some nearest vector. Nearest vector. Let Z is any vector in V and W equal to, I am define I is equal to 1 to N Z comma UI inner product of Z UI into UI. Then Z equal to W plus Z minus W. The same with Z, the inner product is 0. That is, when that inner product is 0 means they are orthogonal. Suppose the W is orthogonal, that is Z minus B is orthogonal complement. The W belongs to this linear span of U, where W linear span. That means W belongs to linear span of S. What about Z minus W? It's complement. Further, norm Z square is this one. We'll see how to put this one. First one, then S is a linearly independent subset of V. See, first I have given S is orthogonal. We'll see proof. 1. S is this one U1, U2, UN is orthogonal set. Is on orthogonal set. The orthogonal set means that is that UI Uj equal to 0 for all I not equal to j. And we know each 0 vector is orthogonal. 0 comma whatever you take, UI is 0 or U whatever. But each vector, okay, whatever you take. This one. So now it's orthogonal set. Now you have to prove this is linearly independent. Now take linear combination, the linear equation. Linear equation. Linear equation. Suppose C1 U1 plus C2 U2 plus up to so on Cn Un equal to 0. This linear equation. If all C1, C2, Cn is 0, then the set is linearly independent. At least one is non-zero. It's not a linearly independent. That means linearly dependent. So now I'm taking say it's a linear combination. That suppose I'm taking this is the linear combination equal to 0. So now I'm taking, suppose you take U equal equation U equal to, so now 0 equal to, can I write 0 comma U 0, what the U is the, so, suppose require this one. Okay, we can take linear span. So now our aim is how to prove this one is the orthogonal to each vector. Suppose we take any UI, 0 can write 0 UI. 0 UI, that means 0 means it's a, C1 U1 plus U2 U2 plus and so on. Okay, you can take CI UI plus and so on CN UN. This one. This is equal to comma this inner product into UI. Now write inner product. This C1 is constant. You can write C1 inner product of U1 comma UI plus C2 inner product of U2 comma UI plus and so on CI inner product of UI comma UI plus and so on CN UN comma UI. See, this orthogonal set means they are each vectors are mutually orthogonal. U1 into UI 0 0 this one. This one also 0. What about this one? Ci into ui into ui. That but it's a it's orthogonal set. That is norm ui square plus and so on 0. That implies ci into norm ui whole square equal to 0. But this vector is never length of the vector. Length of vector never be 0. That equal to ci is equal to 0 for all I. Therefore, C1, C2 all equal to Cn equal to 0. Yeah. That each coefficient are 0 means therefore hence the set S is linearly independent. Li linearly independent. That first part. The next one be on ordered basis. It's a basis. If it's ordered basis, we can write. Suppose V belongs to linear span of S. So now you have to prove this one. If second one, let V belongs to linear span of S, where S is the set of vectors U1, U2, Un. The linear span means therefore V belongs to linear, V is the linear span of S vectors. Therefore V equal we can write some C1 into U1 plus C2 into U2 plus and so on Cn into En for any scalars for Ci belongs to F. This scalars in from field vector. So now you have to find this coefficients. We need to find coefficients. Need to find CIs. So how to find CIs? Now take suppose V into U1. The inner product of V into U1. See, V means this one, C1 U1, or you can write this summation you can use. This what the one? This is a summation I is equal to 1 to n up to n Ci Ui into U1. So now this is the orthogonal set. When you take this inner product, you can, like previous one, you can write this one is C1 inner product of U1 comma U1 plus C2 U2 comma U1 plus and so on Cn Un comma U1. So these are orthogonal means these all are zeros. The mutually orthogonal. That implies we get C1 into U1 comma U1. That is a norm U1 square. That implies C1 equal to inner product of V comma U1 divided by norm U1 square C1. A similar way, we can find remaining coefficients, remaining CIs, remaining coefficients. Riemann coefficient. Yeah, therefore, suppose therefore, so C1 is this one. Whatever C2 is V comma U2 by norm U2 square. Therefore, Ci is equal to V comma Ui by norm Ui square for 1 less than or equal to I less than or equal to n. Yeah, therefore, or hence, V belongs to linear span of S. That implies we write V equal to summation I is equal to 1 to n. So this same thing you can write summation I is equal to 1 to n Ci Ui. Now whatever where Ci is the inner product of V comma Ui divided by norm Ui square into Ui. That is linear span. That is linear combination. Combination of this is some number into Ui. And the any vector in the linear span of the set, this one we can write in this way. This one you can say coordinates of a vectors. Now, what is the third one? In particular, if S is an orthonormal set. See, this one equivalent we can write this one. This is coordinates. See, it's a the third one is simple. Third one A part. S is orthogonal. Orthonormal set. Then the length of each vector is 1 for n. Its length is 1. Each length is 1. Therefore, what is mentioned? Therefore, V equal to, see, its length is 1. Therefore, V equal to the similar way. V equal to summation I is equal to 1 to n in the part of V comma Ui into Ui. This one. Directly. Or you can write this is the each one coefficient, or you can write this is the V with respect to basis. This is order basis. With respect to order basis, we can write order basis. You can write the inner product of each one. First vector, inner product of V comma U1. Next two element, inner product of V comma U2. And so on, inner product of V comma UN. This is order coordinates. Coordinates of a V with respect to basis. You can take this one transpose coordinates. So for example, suppose in the inner product space R3 with standard inner product. Yeah, this set, suppose I'm given set is 1 1 0 1 minus 1 comma 1 minus 1 comma 1 comma 2 is an orthogonal set. So then suppose you ask, then find its equivalent orthonormal set and express some 2 1 3 as linear combination of the vectors of S. So they're asking express linear combination of the vectors of S means it's indirectly it's asking find the coordinates of this vector with this set. Suppose solution, it is simple. Now the first one, suppose find its equivalent orthonormal set. What is the equivalent orthonormal set? Orthonormal set is, what the orthonormal set is? When we get orthonormal set, divide each vector with length. What is the length of this vector? Root 2. 1, 1, 0. Now what is the length of this vector? Root 3. That 1 by root 3. 1 minus 1, 1. Next this length is 4, 6. 4 plus 1 plus 1. Root 6. Minus 1, 1. Yeah, this is the one is corresponding orthonormal set. Now it's asking linear combination of these vectors. See now if it's orthonormal set, the linear combination is v comma ui inner product. So it's orthogonal set, that second part. This is the linear combination. So we get linear combination 2 1 3. What the 2 1 3 equal to summation I is equal to 1 2 3. Suppose we take this is the u1 u2 u3. This is the inner product of 2 1 3 comma ui into ui. You have to write linear combination. That means you have to take each inner product of first vector and that vector. See, if write transpose or not, it doesn't matter. It sometimes I mention transpose or not this way. Like you can write this is a 2 1 3 equal to. See now we check the first inner product of first vector. What is inner product of 1 into 2 2. 2 into 1 1. That is 3 and divided by, okay, norm ui square. Norm ui square. Yeah, what is the inner product 2 1 3 into the first vector? 3. 3 divided by norm, the length is 2 into 1 1 0 plus, next what is the inner part of second vector? 2 minus 1 1. 1 plus 3 4. 4 by 3 plus 4 by 3 into 1 minus 1 1 plus, next this vector into u3 minus 2 plus 1. Minus 2 plus 1 is minus 1. Minus 1 plus 6 5. 5 by 6 minus 1 1 2. Now you can write this linear. You can check any doubt, you can add this one, you get this one. So this one, this is the coordinates. You can say 3 by 2, 4 by 3, 5 by 6 is coordinate vector of 2 1 3 with respect to this set S. It's a basis with respect to this basis. So now you can check that if any doubt, 3 by 2 plus 4 by 3. 3 by 2 plus 4 by 3 plus minus 5 by 6. Now we can take this one. This LCM is 6. 9 plus 8 minus 5. 9 plus 8, 17 minus 5. 12. 12 by 6, 2. That's a 2. Now 3 by 2 minus 4 by 3. You can check. 3 by 2 minus 4 by 3 plus 5 by 6. Again, that must be 1. The 6, 9 minus 8 plus 5. So 1, 6. 6 by 6, 1. Again, you can take the third element. That means every vector we can write linear combination of linearly. Every vector we can write linear combination of a orthogonal set. So now here length is 1. You can go for this one. You take u1 u2. Suppose this vector is length is 1. You can use this relation. If length is not 1. This is the one. Yeah, this is we are explaining linear combination. Yeah, these are the coordinates. Now what are the coordinates? Yeah, this one is coordinate vector of this one. So it's asking find the like find the coordinates of 2 comma 1 3 with respect to the basis 1 1 0 1 minus 1 1 minus 1 comma 1 comma 2. So it's asking like this. Find the coordinates of these elements with respect to the basis. What are the coordinates? The 2 1 3 with respect to basis. Suppose you take basis this one. The coordinates with respect to this one. You can write the same. We'll get this one coordinates. That the coordinates means inner product of this vector into this one. This vector directly you can write. Coordinates are inner product of 2 1 3 into 1 1 0 comma 1 minus 1 1 sorry 2 1 3 1 minus 1 1 2 1 3 minus 1 1 2. This is the coordinates. The base is that one. So now we'll know this one. You get 3 by 2, 4 by 3, 5 by 6. This is the coordinates. So it's given transpose. You can write each one. You can use transpose. Find the coordinates of this one. You can write this one transpose. Each one is transpose. These are the coordinates. The transpose is doesn't matter. If you can write the vector in row wise or column wise, both are same way. This is the one. So now we'll see another third one. Second part, nearest vector. Let Z is any vector, Z belongs to V, and W equal to this one. I is equal to 1 to n, Z Ui into Ui. The inner product of Z Ui, we are defined W. This one, the inner product is this is 0. See now last, the third one, third B, given V belongs to Z. Here Z belongs to V and W equal to, we define summation I is equal to 1 to n Z comma Ui into Ui. W is W is the linear span of S. This is, Ui is vectors in S. W belongs to linear span of S. See now we have to prove this is orthogonal. See, now we are writing Z equal to W plus Z minus W. The Z minus W is orthogonal. Now we take, so now proving this one. So note that one, suppose take 1 less than k less than equal to some number lies between n and n. So now Z minus W. Now take any vector. Okay, this equal to Z comma UK minus W comma UK, where W is the summation I is equal to 1 to n Z Ui Ui. That's a linear span of Ui. See now this equal to Z comma UK minus summation I is equal to 1 to n Z comma Ui Ui comma UK. See now here Ui, this Ui is orthonormal set. Orthonormal set means, see this one same as you can write Z comma UK. This is some number you can write outside. I is equal to 1 to n Z comma Ui. Inner product of Ui comma Okay, the same as correct. Z comma UK minus this is correct outside. It's some number Z comma UI. Inner product of UI comma UK. So this is orthonormal set. This k is less between 0 to n. At kth element is non-zero. Remaining all are 0. That means we can write Z comma UK minus this all are zeros. At kth element is non-zero. That means this one Z comma UK. At kth element this is the orthonormal set. Since UK comma UK, this is the norm UK square. This equal to 1. That means this one. This equal to 0. Yeah. Therefore, Z minus W belongs to linear span of S pair because W is the linear span of S. That means each vector in W. Hence, that means in the inner part Z minus W comma W equal to 0. As we know, this one W belongs to linear span of S. That one. See now this one. See, Z minus W belongs to this Z minus W is orthogonal complement of W. Yeah, further, then now we have norm Z square. See, we are taken Z equal to this one we can write norm Z equal to Z minus W whole square plus norm W square. See now, if you take this inner product, this is always greater or equal to norm W square. That means, yeah, you can use that inner product. When you write this one inner product, norm Z square is this one. Generally, just I give idea. This is a norm Z square equal to norm of this one. See, this norm Z minus means inner product of Z minus W comma Z minus W plus norm W square. Okay, write this one. We know Z equal to Z minus W plus W. That norm Z square equal to that inner product of Z minus W plus W comma inner product of Z minus W comma W plus W. Now take this inner product Z minus W Z minus W and Z minus W into W. This inner product because here you have to use this orthogonal Z minus W comma W. This is now use this result Z minus W comma W is 0. Using this result, this equal will get norm Z minus W whole square plus norm W square. See Z minus W whole square into plus norm W square. This is always more than W square. This is the result. You can use the inner product definition. We'll get this one. I have to use this condition Z minus W comma W. Now we know when you write U already we discussed projection. U equal to we can write U minus in the part of V comma U and norm U square into U plus in the part of V comma U norm U square into U. So this is the project the same as U minus P plus P. Therefore this is this one is the projection of V onto U. See now, this is a projection. Now, in the general, that means the projection. See now, this is the perpendicular, that complement. That means perpendicular. See that means this is orthogonal to this one. The projection we know this is actually this is the error vector. We already know the error vector is orthogonal to projection vector. That's why in the general case, we have written z equal to z minus w plus w. We written this one. See where w belongs to linear span of S, where w belongs to linear span of S is the, see now here is the projection of this one, is the projection of, see now here, see this one is the projection of U, projection of V onto U, is the projection of Z on the space linear span of S, and this one is the Z minus W is orthogonal to linear span of S. This is orthogonal. Further, observe that one. Further observe that now each of the vectors, that one Z comma ui into ui is the projection of Z onto the vectors ui for 1 less than or equal to I less than or equal to n, and here w is the, where w was their sum, here w is their sum. But w means a linear span means sum of the combination of the vector. This is the one. See generally the projection that you use, that one next one, you take u minus that projection, this is orthogonal to next vector. Suppose if you take u1 u2, suppose any two vectors, so we want to find other this u1 u2, if take u2 minus the projection of u1 onto u2, projection u2 onto u1, that means inner product of u2 comma u1 by norm u1 into u1, projection of u1 onto u2, this is orthogonal to u1. This is the main thing. Okay, next we'll discuss this one. Now I stop here. Thank you.